All right, class. So if you go to the Moodle page, I know you can't see most of this right now. This is not what your Moodle page looks like. This is what my Moodle page looks like, but you will be able to see this. You're going to click on this hydrogen atom wave functions. It's going to take you to this website that was created by a professor at St. Olaf College. And so we're going to explore, we've talked about the hydrogen wave functions, we've explored them mathematically. Now we want to explore what they look like visually in 3 dimensions, which you all know I can't draw. So we're going to use this nifty little web app to plot some things. And so we're going to go ahead, and here you have in this corner up here where my mouse is, you can choose your value of n. So we're going to start with n equals 1. You can choose your value of L. It won't let you choose any value but 0 right now because I've selected that n is 1. But if I were to go to n is 2, now it will let me go to L equals 0 or 1. And it will let me change m sub L from -1, 0, or 1. So it won't let you choose invalid options or combinations of your quantum numbers. So we're going to go ahead and update orbital. Ooh, so right below update orbital is a sort of list of options. Right now, this is a phase point list, and so you can click and you can drag this around, but maybe you don't like looking at a whole bunch of little dots. That's not my favorite way to look at orbitals. So another way that we can do this is an isosurface, which is one that I particularly don't mind, or the wireframe. So wireframe is probably the one that I find easiest to look at. But you can play with those options. So the n equals 1, L equals 0, m sub L, or m equals 0, looks exactly like a 1s orbital, which is exactly what we would anticipate it looking like. And so we can go, let's say n equals 2, L equals 0, m equals 0. We'll update the orbital. It's also going to stick with wireframe. You've noticed that the color has changed, right? And so one thing that this is going to do, color changes between blue and red signify negative and positive. So we can go to n equals 1. We'll keep it at m equals 0. So this should be aligned along the z-axis. And it should be a p orbital. Let's see if we can zoom out a little bit. Yes, you have some options down here. You can zoom in and out below the XY plane. You can also change the transparency if you wanted to see through these a little bit. So you have options to play with here. This is probably where I would like, exactly as we expect, we see that this is aligned along the z-axis. Blue in this case is positive. You can see it's aligned to the positive. Red is negative. Okay, so let's play with a few other things. We're going to go back to our nifty 1s orbital for now. Beautiful. Okay, so let's see what other options we have on the screen. We also have this plot over here, which right now is showing nothing. We're going to ask it to show a radial plot. And we have some different ways that we can plot this. So we'll start with R. So one option is just plot the radial function. And so this is your R axis, or distance on the bottom from the center, from the nucleus. And the vertical axis here is the intensity or height of your wave function. So your radial wave function looks like an exponential decay, which if we go back and remind ourselves what that first radial function looked like, it did mathematically look like an exponential decay. So this makes some sense. So this is looking at the actual, just the radial component of the wave function as it stands. So let's undo that. Let's put r squared. So r squared is going to be the radial function squared. So normally when we think of squaring a function, we think about that as being probability. Another useful way to think about the wave function squared, however, is little r squared, because that's actually what shows up inside the integral that we would integrate to see probability. So it actually effectively is probability when we're in spherical coordinates, is thinking about that r squared sine theta times our total wave function. And if we're just dealing with the radial component, we don't have that theta, so we'll just look at little r squared times large r squared. And we get something interesting. So we have 0 probability of finding the electron at the nucleus, at the center. That makes sense, right? Because if it makes it to the nucleus, those two charges will connect and negate one another, right? We will no longer have an electron in a nucleus separate. But we do see that we have a high probability, the maximum probability, in fact, of the electron. Looks like it's somewhere around 0.5 angstroms away. So you can actually click on this plot and see what the probability function is at different places. So you can actually see where this is relative to, oh, it's storming outside, sorry, I got very distracted there. Relative to the circle that we're seeing. So the gray circle was the wire mesh that we were seeing before. And you can see that as you click further and further out, you're seeing more and more of that. I don't know what the colors are inside, I'll have to look into that. But the highest probability is actually quite close to the center. It's pretty far inside that wireframe. Is where you have your maximum probability. But normally what we plot with this wire mesh is quite a bit more, right? So this is the 90%. There's a 90% probability of finding the electron here. And 95 is out here. And both of those are pretty close to sort of your total that we're plotting all the way out. So we can also do this with some other functions. And so the activity I'm going to have you do is going to be to play with different orbitals. So again, you're using this menu up here to change your orbitals. We're going to go back to it being a wireframe. And to have you play with some radial plots. I want you to really investigate what some of the trends are for your radial plots and for your orbitals that you're looking at. And these orbitals should look familiar because we looked at them a couple weeks ago in class together when we looked at the spherical harmonics and those shapes, but you've also seen them before, right? General chemistry, you saw them. You may have seen them in other contexts in other chemistry courses. And so I will leave you to playing with this. Just for the record, if you have trouble seeing against the white background, you can also change the background to black. I find the white background is a little bit easier to see with the wireframe, but if you're looking at other types of plots, it might be easier to change the background color as well. So go to the Moodle page. Your next step is to find and complete the activity called Exploring the Hydrogen Wave Functions Graphically. Remember to post questions, comments, and random discussion to the class discussion project or channel on the Slack page.